we're going to move on and have a look at how we can calculate a multi-stage liquid-liquid extraction system. So that's called the Hunter-Nash method. And then I'm going to let you have a go at doing an example of that yourself. And then I'll go through some concepts around liquid-liquid extraction general design. So hopefully you should remember from last week that when we were thinking about a single-stage liquid-liquid extraction system, the first step that we did was to actually calculate an overall mass balance for the system. So we can do exactly the same with a multi-stage liquid-liquid extraction system. So in this case, our overall mass balance is still given by the feed and the solvent added to the system, and it's still given by our raffinate and extract product. But in this case, what we've done is we've defined essentially a stage N. So our final output raffinate is Rn, and we've also defined a stage 1. So our extract is E1. Okay, so that's essentially what we've done there, is define that like you do when you're looking at distillation. So with the McCabe-Fill method, you have a number of stages. We can also have an overall balance on the component as well. So for each component going into our system, we expect the same total amount to come out. And that's because we still don't have any kind of reaction occurring in our extraction system. So as well as that overall mass balance, we can now have a mass balance on a particular stage. So if we concentrate on our general stage N, again, what we know is that what goes in must come out. So our Rn minus 1 plus our En plus 1, which are the two streams entering that stage, must equal En and Rn, which are the two streams exiting that stage. So with liquid-liquid extraction, a useful thing to then do is look at what's called the difference in flows. So we can actually rearrange our mass balance for our general stage N into the form of the difference of flows. So what we end up with is that essentially our left-hand side set of flows, our Rn minus 1 minus En, also equals the difference in flows on the right-hand side. So our Rn minus En plus 1. And then we can define that difference in flows as a point delta. If you think about this in a logical manner, because this flow difference in flows is equal to this difference in flows, and this difference in flows is essentially what enters this stage, so this difference in flows again must be the same as all the others. So for every single stage in our liquid-liquid extraction system, this metric of that difference in flows is identical. So for every stage, we have a common value of delta, okay? And that's important, and we'll see the use of that as we move on. So unsurprisingly, after doing a total material balance, we can also do the same for a balance on our components in the system. So in this case, we have the amount of an individual component entering our stage N is equal to the amount of each individual component leaving stage N. And again, we can rearrange this to give the difference in the component flows. Okay? And again, that difference in component flows must be the same for every stage in our liquid-liquid extraction system. So as we did when we were thinking about our total mass balance for our single stage system, we were able to rearrange the expression for the mixing point to show that it's a straight line. So in this case, what we can do is we can rearrange our expression for our delta point to actually give us the same expression as a straight line. Okay? So what we're showing is that for every stage, the set of component flows, if you draw a straight line through those two flows, they will all pass through the same common point. Okay? So we can define that as an operating point. Yep. And this will help us design our liquid-liquid system. So if you remember going back to distillation with McCabe-Thiele, you have an operating line. If you looked at the Ponchon-Savray method for distillation, you get an operating point. So this Hunter-Nash method is similar to that, and you get a key operating point. And what we'll do is we'll look how we actually use this operating point to design our multi-stage system. So if we just think about it conceptually first, before we start to draw it out, we know that each end of our stage is linked with an operating point. So we essentially can link these, our initial, for our input to stage 1, with an operating point. We then know that for each stage, our extract and our raffinate must be in equilibrium with each other. Okay? So we can link these with our equilibrium tie lines in our system. We now know one of the components on the left-hand side of stage 2. And again, we can link the left-hand side of stage 2 with knowledge of our operating point. And then, again on stage 2, our extract and our raffinate must be in equilibrium with each other. So we can link that again by our equilibrium line. So you can see how similar to when we're designing distillation systems it is. We have an operating, then equilibrium, operating, then equilibrium. And we can repeat that for the whole system. So let's bring back the example that we looked at last week when we were just thinking about a single stage system. So if you remember, we had 400 kilograms of our feed, and our feed was 25% solute and 75% carrier. And we also had 100 kilograms of our solvent. So the first thing that we did, and it's the first step that we still need to do with our multi-stage system, is to look at that overall mass balance. So essentially, we want to find the mixing point. So last week, I showed you how we could find that mixing point using the lever arm rule. and said that you can also find that mixing point via a mass balance. So if we did a mass balance, then we would find that we have 20% of our solute, 60% carrier, and 20% solvent at our mixing point. So we can plot that mixing point onto our diagram. So when we looked at the single stage extraction, we were constrained by then considering the direct split due to the equilibrium tie lines. However, because we now are thinking about a multi-stage system, we're not constrained by having to use that equilibrium because we've got multiple stages of equilibrium. And the advantage of that is that we can actually define our own raffinate composition. Okay? So if we're told the purity that we want, we can actually define our own raffinate composition. If we define our raffinate composition as 2.5% of our solute, so we know that we can, if we want to plot this point on our diagram, then we know because it is one of the equilibrium phases that we have to draw that point on the equilibrium curve. Okay? We also know that the raffinate is on the feed side of our diagram, and we also know that it has 2.5% solute in there because that's what we've picked. So there's essentially only one position that satisfies all of that criteria, and it's there. Okay? So what we can do is we can actually use plotting that point now to read off the compositions of the other component in our raffinate product. So our carrier, which is our C, this corner, that is about 92%. And our solvent, which is this corner, is about 4%. Okay? So the next thing we need to do is find our extract point. Okay? So we know that the overall mass balance for the system, our raffinate plus our extract must give our mixing point. Okay? So because it's a mass balance, we know that they all must lie on the same straight line. So what we can do is draw a straight line from our raffinate point through our mixing point until it reaches the other side of our equilibrium curve. Okay? And that is our extract point. Okay? So that allows us to actually find the raffinate and the extract for our multi-stage system. And again, we can read off the compositions of our extract component. So it's almost 46% of our solute, about 12.5% of our carrier, and about 42% of our solvent. So if we wanted to, we could then either carry out a mass balance of our extract and raffinate with those compositions to calculate the total flow rate, or we could use the ratio of the length of the lines from E to M and M to R to use a lever arm rule to calculate those flow rates. Okay? So because we looked at that before, I'm just going to write down the values. So it's almost 300 kilograms in the raffinate and just over 200 kilograms in the extract. So now what we've done is defined the separation that our multi-stage system is doing. So what we need to do is now move on and find out how many stages we actually need in our system. So for clarity, what I've done is I've just removed the mass balance lines so that they don't get in the way of the next set of lines I'm going to draw. But I've left on the key points: the solvent point, the raffinate point, the feed, and the extract. Okay? So when we looked at our multi-stage system, we defined this definition of the concept of the difference of flows. Okay? So that concept of the difference of flows gave us an operating point. And what we said for those difference in flows was that the operating point must be the same. So if we think about our ends of our system, i.e. our final raffinate product and the feed, and our extract and the solvent, okay, they're our extreme ends. So we would know that the extract and the feed and our operating point all lie on a straight line. And our solvent and our raffinate and our operating point, again, all lie on the same straight line. Okay? So that's, to remind you, we've got our solvent, raffinate, our extract, and our feed. Okay? So that's our operating pairs. So because we know all these points, what we can do is simply draw straight lines between the value points that we know, and where those lines cross, we get our operating point. Okay? So we can draw a point for our extract and our feed, and we can draw a line for our solvent and our raffinate, and then where those points cross, we get our operating point. Okay? So now, if you remember back to what I was saying, we can then use that stepping method to define the number of stages in our system. So we link our feed to our extract via our operating line. Then we go from our extract 1 to our raffinate 1 by an equilibrium separation. So what we can do is use the tie lines on our system to define that separation. So that would be our R1 stage linked to our extract via our equilibrium. Then we then link our, So what I've done is I've estimated that based on the tie lines, the equilibrium tie lines. So you can see it's much closer to this top tie line, maybe 25% to 75%. So I estimated the same 75-25% on that bottom. Okay? So then, when we've got our raffinate to our actual, out of our first stage, we then again know we can link that to the extract from the second stage using the operating line again. Okay? So what we do is we use our operating point and our raffinate composition, and we draw this across, and we can define our second extract point. Okay? Then again, we know that for stage 2, the extract and the raffinate for stage 2 must be in equilibrium with each other. So we can find our next raffinate point by using our tie line data again. Okay? So does that make sense? That we go operating line, equilibrium line, operating line, equilibrium line? Yes? No? Yep. So, okay, yeah, so we know that the next extract must be, due to the flow difference, must be joined using the same operating point, okay? And we also know that because our extract is an equilibrium component, it must lie on the equilibrium line of our system, and it also must lie on our solvent side of the diagram. And because we know our R1, we were able to draw a line from our operating point through R1 and take that all the way across to the extract side of our diagram. Okay? So it's the same process as for distillation. So for distillation, you step essentially up to the equilibrium and then across to the operating line, up to the equilibrium, across to the operating line. In this case, we join our points with the operating line, then we use the equilibrium tie lines, then we use our operating line, then we use our equilibrium line. Okay? So what we can do is essentially continue this process. And just like in distillation, we stop when we get past or to our point that we actually pick. So in this case, when we get to our defined raffinate composition, we stop this process. Okay? And then, so now we've drawn our system. So what we need to do is actually now count up the number of equilibrium stages that we have, which defines how many stages we need in our system. So to do that, we just pick our equilibrium that we've drawn. So in this case, our red lines, we know that there's 1, 2, 3, 4 of them. So we know that our separation needs 4 stages. Okay? So what we've done there is we've essentially used our ternary diagram to design both the mass balance for our multi-stage system and calculate how many stages we need for our multi-stage system. So when we're designing our liquid-liquid extraction system, we've got some choices that we can make. So the first one of those choices is whether we just need a single stage equilibrium, or whether we need a better raffinate product. So we would then think about doing a multi-stage system. And that's what we've been looking at. So we have a multi-stage system, but we only have a single section. Okay? Now, if you've noticed, in the example that I did and the question that you've been attempting is, although you get a free choice of your raffinate, you've been able to specify your raffinate composition, your extract composition is actually determined by a straight mass balance through your system. Yeah? So you don't have a free choice of your extract. So if you want a free choice of your extract as well as a free choice of your raffinate composition, exactly like you do in distillation, yeah? So in distillation you can pick your top product composition and your bottom product composition, not just one of them. So if you want a free choice, then you have to think about adding a 2-section cascade system. So in that case, you would add your feed, but you see that that's actually a different position to where you get your extract from. And you would actually have a reflux of your solvent passing through the system. Okay? So next week, we'll actually have a look at how you might go about designing this 2-section cascade system. Okay? And as well as having essentially where you just add your solvent and then you recycle some of your extract, you can actually use a dual solvent system. So if you're struggling to get the composition you want, or you have a more complex liquid-liquid system, you can actually use a dual solvent system where one of your solvents preferentially dissolves the solute and another solvent actually preferentially dissolves your original carrier. Okay? So that's a much more complicated system, and that's a possibility that you can have. So when we're thinking about actually designing one of these systems, we can think about our entering feed flow rate, our composition, the temperature, and the pressure. Okay? So normally, your feed flow rate and composition are fixed. You can't do anything about that. Okay? Your temperature and pressure, you can change. But remember, it's liquid-liquid extraction. So, it needs to be a liquid. Yep. But beyond that, the pressure only has a very minor effect on the solubility. However, the temperature does have an effect on the solubility. So you might be able to change the exact position of those tie lines by slightly changing the temperature. Okay? But as I mentioned right at the start of this course, heating and cooling unnecessarily is expensive. Yep. So you would only want to think about that if you really had to, or you were very close to being able to get the composition you needed, and a little tweak in temperature would actually affect the tie lines to allow you to do that. So as just mentioned, when you're thinking about designing a liquid-liquid extraction system, you can have a 1 or a 2 section system. Okay? So that's up to you. So that depends. So you might have a specification for your raffinate, and if the extract that comes out is okay, based on a single stage system, you would have that. But if you need to get that extract composition to be changed to affect your recovery, then you might want to think about a 2 section system. And again, that affects, as I say, your degree of recovery for your solvent, your solute, and your carrier. And if you're having a 2 section cascade, you need to again think about the degree of separation that you actually want for your feed. So the other 3 choices that you have, and a big choice for liquid-liquid extraction, is what solvent you're going to pick. Okay? So you want to pick your solvent based on having a good solubility with your solute, but essentially being unsoluble, immiscible with your carrier. Okay? So if you look on Blackboard, there's a short few slides actually discussing how we would select our solvent, and they go through and show you how you would actually select a solvent. Again, you've got your operating temperature and pressure of the actual column. Okay, so you can pick that again to optimize the equilibrium between the feed and your solvent. And then, just like in distillation, we have a choice of a solvent flow rate. So if you add more solvent, it's highly likely you're going to get a better separation. And if you add more solvent, it's more than likely that you'll reduce the number of stages you need. But by having more solvent, you can have a higher operating cost. Okay? And then by having more stages, you have a higher building cost. Okay? So again, like in distillation, it's a balance between the solvent ratio and the number of equilibrium stages you have. So with liquid-liquid extraction, there's a few other sort of options that you need to think about when you pick your solvent with your feed and design your system. So the first of these is that, as mentioned, you have to actually mix your solvent in with your feed. So you have to mix it together to form, so you can increase that mass transfer. And by mixing it together, you form an emulsion. Now, if that emulsion is really stable and doesn't want to separate, then that's really difficult for your liquid-liquid extraction system, because you've got to wait a long time for it to actually phase separate. Okay? So you need to think about the separation by gravity of those of the solvent and the carrier. If you've got any impurities in your system, you can get some scum formation, and that's essentially like a little foam waste material, and that can actually block up your liquid extraction column. Okay, so you need to think about any impurities that you might have in your system. The interfacial tension essentially links to the emulsification. So the higher the interfacial tension, the more difficult it is to actually make a good emulsion and to actually mix your systems together. So if you pick a solvent that has a really, really high interfacial tension, you're going to need to put a lot more energy into your system to actually mix the solvent with the carrier. Okay? So so you need to think about that for cost. Also, a phase density difference. So we're separating our mixed phase essentially by gravity separation. And to separate by gravity separation, you need to have a difference in density between the carrier and the solvent. So if you find a really good solvent, but it has exactly the same density as your carrier, then you can't separate them by gravity. Okay? So you also need to think about, as well as your solvent being immiscible with your carrier, you need to make sure that the density of the solvent and the carrier are actually different. And then you want to think about a resonance time in your system. So how long is your material actually in your liquid extraction system for? Is it in there so long that you potentially get some degradation of your product? And that will be linked to the temperature you're running at and how close potentially that temperature is to the decomposition temperature of one of your materials. So in that first week, we thought about penicillin, and that decomposes around 50 degrees, 55 degrees. So if you're separating that with a liquid extraction system at 20 degrees, it's probably not a problem to hold that at 20 degrees for a long period of time. But if you're having to do your liquid extraction at 50 degrees, right, which is very close to that decomposition temperature, the longer that stays at that hot temperature, the more likely it is to start to degrade. Okay? And then essentially all of these come together in terms of the cost and the power requirements, and then the different types of extractor that you can look at. So for liquid extraction, the equipment is essentially similar to that of an absorber column or a stripping column. And often these very just the packed columns or stage columns are quite inefficient unless the liquid viscosities are very low and there's a very big difference in the density of the phases. So you can start to enhance this separation by adding some kind of mechanical or centrifugal devices into our column. So we may have a mechanical, at least mixed section that actually helps to mix the components together, and then that may be followed by a centrifugal style section of the column that helps to separate the components. And then this may go back into a mechanically mixed section for the next stage, and so on up the column. But regardless of the type of equipment that we actually use, the number of equilibrium stages, so that's what we've just looked at calculating with the Hunter-Nash method, we need that information first. Okay? So again, on Blackboard and in the notes, there's some information about the different types of extractor systems that we can actually use. So when we've got this number of stages, what we can do is very similar to just the packed column that you looked at for distillation, is essentially use this height equivalent to a theoretical plate. Okay? And for some reason in liquid-liquid extraction, they sometimes use hept instead of hept, which is height equivalent to a theoretical stage, but they're essentially the same metric. So it's how high in amount of packing, or how high in amount of the packing with mechanical agitation added do you need to get one theoretical stage of separation. And then to get the total height of the column, we actually take essentially our number of stages, our number of transfer units that we've calculated using the Hunter-Nash, and just times that by this height of a theoretical plate. Okay. And it's typical to describe the dispersed phase, so the phase that gets mixed in as droplets, as the discontinuous phase, and then the other phase, the phase that those droplets are mixed into, as the continuous phase. And depending on the mixtures of liquids that you have, either the carrier or the solvent can be either one of those phases. Okay? So I've got with me, and you're welcome to have a look during the tutorial session, but I've got a few different packings with me that are used in liquid-liquid extraction, so you can just have a quick look at some of the packings, and I don't know how visible this will be. So this is a structured style of packing. You can see it's essentially made up of angled plates, and then you pass your system along these angled plates, and then you just pack your whole column. And the key things with the packings are essentially, if you remember from distillation, the voidage in your system, and then how much surface area you actually have. So you can see here that actually there's a whole, there's a whole variety of different materials that your packing can be, okay? And all of these materials can actually be used in a commercial packing, and you need to think about what liquids you have and what packing you need. So this is a glass packing, a borosilicate glass packing, okay? So you might use that for a very reactive system, because glass is very non-reactive. This is a metal packing. Okay, it's often the cheapest type of packing, but if you've got any liquids in your system that might be slightly reactive, then they're generally reactive with a metal, so they may start to degrade or erode or actually completely destroy your metal packing. And then the final one is a ceramic style of packing, and ceramics are very good at very high temperatures. So if you're having to do a separation at very high temperatures, then you might want to think about a ceramic style of packing. A number of you might have noticed that next week is the coursework. So the coursework will take part as a short online test. Okay, so when you start the test, you essentially have an hour to complete the test. I think last year's average completion time was about 20 minutes, so there should be plenty of time for you to do the test in. So, and some of you have already asked and have noticed the fact that the deadline for that test is on a Sunday at 8 p.m. The test will be open from Friday morning until Sunday at 8 p.m. The reason that it includes the weekend is because of the industrial experience students who are working during the week, so they need to have access at the weekend as well. So you can take the test any time in that time period that you want. The style of the questions are the same as those actually in the practice tests. There was one last week, and there's also one, there was one the previous week. So you can look at those same style of questions. The practice ones are just available on Blackboard. They're open all the time. You can do them as many times as you want, but they let you see the type of questions that are coming up in the coursework. The other thing I'd like to point out for liquid extraction is that you'll notice in between weeks 4 and weeks 5, there is a link to a web app on liquid extraction. This goes to a page where is essentially a variety of practice questions. So you're welcome to use this and have a look at a variety of questions. So there are the same style as in the handbook and the same style that will appear on the exam, but essentially it generates a set of questions, and then you can essentially put your points on exactly how you would actually plot by hand to allow you to practice this style of questions. Today, we essentially looked at how you might think about designing a multi-stage liquid extraction system, and we looked at the Hunter-Nash method, which actually allows you to calculate the number of stages you need in an extraction system. So next week, we're going to look at how we would move from a single section system to that double section system where we can actually specify both our raffinate and our extract product.